In this video, we'll talk about properties of a uniform circular motion. So first, what is uniform circular motion? So let's say an object moves along a circular path, and the object, let's say, start from here and move with a constant speed, or you can say constant angular speed along this path. Then it's called uniform circular motion. Okay, so let's write down these conditions. So the speed of the object is a constant, or you can say the angular speed is a constant. And let's first build a coordinate system to describe this motion. The center of the circular path is O, and I'm going to use O as the origin of the coordinate system. So that's the x-axis, and the y-axis is along this direction, and 90-degree angle is the x-axis. And the particle starts from here, and we want to say this instant is 0 second. So we start counting time right at this instant. Suppose the object is here after a time t. So its velocity, its position vector is given by this vector r, and its velocity at this instant is along this direction. Okay, tangential direction. We'll talk about its velocity in a separate video. Now let's say the position vector has coordinate x and y at this instant t. Now let's calculate what is the expression for x and y as a function of time. Now I want to denote this angle as theta. Okay. Now theta is actually a function of time, and it's given by omega times t, since omega is a constant angular speed. Now let's write down the position x and y in terms of radius r. R is the radius of the circular path. So x equals r times cosine theta. And since theta equals omega t, so x equals r cosine omega t. That's the x component of the position vector. Now the y component is given by r sine theta, which is r sine omega t. Okay, so now we already know the position vector of this object. Now let's take a derivative of these two quantities, and we can get to the velocity information. So Vx is dx dt, the derivative of position with respect to time. Now cosine becomes negative sine, and there's also a factor omega, negative omega r sine omega t. Now Vy is dy dt. So we similarly get omega in front of the expression, and sine becomes cosine. So that's the velocity, x and y component. But if I take a further derivative, then ax equals dvx dt, I can calculate the acceleration. Now sine becomes cosine again, and bringing out another omega, negative omega square r cosine omega t. ay equals dvy dt equals, now cosine becomes negative sign, and there's an additional factor omega, sine omega t. Okay, so that's the acceleration. Okay, so that's the expression for position, velocity, and acceleration of an object doing uniform circular motion. In the next video, we'll talk about velocity, acceleration, etc. in detail.